In this example, we're going to find the limit as x goes to negative 3 of 4x minus 5 over x squared minus 9. All right, so this is the limit as x goes to negative 3. So the very first thing that we are going to do is to plug in the negative 3 there and see what we get. So when we simplify that out, we get negative 17 over 0. So what we've wound up with is a non-zero number, negative 17 over 0. So we know that the answer is going to be either infinity, negative infinity, or it does not exist on the answer here. Okay, so what we need to do then is to take a look at what's going on with the bottom part. How is it going to 0? Is it going to 0 through positive numbers or negative numbers or both? We know what's going on with the top, right? The top is negative, and it's getting closer to negative 17 the closer x gets to negative 3. So just really need to analyze the bottom, and what we need to do is to solve this inequality, x squared minus 9 greater than 0. And we don't really need to go through the whole way and solve this out, but the process of solving that inequality is going to help us get the answer here. All right, so how do we solve an inequality that looks like this? Well, this is a quadratic inequality. X squared minus 9 is a quadratic function, second degree polynomial. So what we're going to do then is to set it equal to 0 and solve this out. So this quadratic equation is one of the easier types of quadratic equations because it's missing the x term here. It's just x squared and the constant 9. There's no x term in here. So what we want to do is to isolate the x squared part by itself. Just get x squared on one side and a number over on the right hand side and use the square root property. That is, if x squared is equal to 9, then x has to be equal to plus or minus the square root of 9. And of course we can simplify the square root of 9 to 3. So we wind up with two solutions to this quadratic equation. We have x equals 3 and x equals negative 3. All right, so to continue on solving the inequality, what we would do is take those numbers and put them on a number line. Okay, so negative 3 would be to the left of positive 3. Here we had two solutions to the equation, so that breaks the number line up into three pieces, right? This piece here to the left of negative 3, this piece here in between negative 3 and 3, and this piece here to the right of positive 3. And so what we're going to do is to pick test points in each one of those intervals there. And you can pick anything you like as long as it belongs in there. I'll pick negative 4, 0, and positive 4. All right, so next I'm going to take and substitute those values into the inequality. X squared minus 9 greater than 0. That's the inequality that I'm trying to solve. So first off, I am going to substitute a negative 4 in for x and see what I get. Keep solving that out. Negative 4 squared is positive 16. And I wind up with 7 is greater than 0. So if you were after the solution of the inequality, if that's all you cared about, then you would know that not only is negative 4 a solution to that inequality, but every piece there on that, or every number in that on that piece from to the left of negative 3 would also be a solution. But what we really care about here is whether or not those numbers on that piece to the left of negative 3, when we substitute them into x squared minus 9, whether they're positive or negative. And here you can see that I got a positive 7, right? So that means that I would get a positive on this piece right here. So in other words, not only when I plug negative 4 into x squared minus 9 will I get a positive number, every number on this piece, right, to the left of negative 3 will, when I substitute any of those numbers in, I will also get a positive in x squared minus 9. So, all right, next up I would do the same thing with 0. Substitute 0 into the inequality, and here I get a negative 9. So that indicates, hey, when I plug in a 0 into x squared minus 9, I'm going to get a negative. And not only that, every number, right, in this interval here from negative 3 to positive 3, when I take any number from there and put it in for x, I am also going to get a negative. So Just make a little mark there to that effect. All those numbers, when I plug them into x squared minus 9, I'm going to get a negative number. And for the 4, it's going to be exactly the same calculation over here. When I have a positive 4 squared, I'm going to get 16 minus 9. So I'll get a 7 again over there. So that is also a plus. Okay, so I've made a sign diagram essentially there for the x squared minus 9, which was the bottom part, right, of the original function that I had, that I was taking the limit of. Okay, so now I have the sign diagram, and that will tell me everything I need to know about the limit that I'm after here. I'm going to take a look at the one-sided limits first, and then once I know what each one-sided limit is, then I can make a conclusion about what the two-sided limit is. Okay. All right, so recall that when I substituted the negative 3 into this function, I wound up with negative 17 over 0, right? And so I know the top part of that would be negative, and then it was a matter of, well, the bottom part is going to 0, but is it going to 0 through the positives or negatives? And as I'm going to negative 3 from the right, on the number line, negative 3 from the right would be over here. So I'd be in this region. The x values would be getting closer and closer to negative 3, but over here on the right, and on the right, those values, when I plugged them into x squared minus 9, would give me a negative number. So I'd wind up with a negative on top and a negative on the bottom for all of those values that as I'm getting closer and closer to negative 3 on the right. So what that indicates then is because a negative divided by a negative is positive, the answer here for this part, the limit as x goes to negative 3 from the right of this function, would have to be positive infinity. All right, next up, I'm going to take a look at the limit as x goes to negative 3 from the left of the same function, and I'm just going to go through the same analysis. I know that I had negative 17 over 0 when I plugged in, so I know the top part would be negative, the bottom part was going to 0, right? And so I just needed to figure out how it was going to 0, so again, the sign diagram is going to give me that answer. Here, I'm going to negative 3 from the left, right? So it'd be over here on the left side of 3. And for any x that I pick over here, even as I get closer and closer, when I plug those into x squared minus 9, I'm going to get a positive, right? So on the top, I'll have a negative. On the bottom, I'll have a positive. So negative divided by a positive is a negative. So the answer has to be negative infinity on this one. Okay, so now I know both of the one-sided limits. That lets me calculate the two-sided limit. Okay, so, and that was the original problem that I wanted. The limit as x goes to negative 3, not the one-sided or two-sided, but, I mean, not the left limit or the right limit, but the two-sided limit. Okay, and I know that the limit from the left, one of them was positive infinity and the other was negative infinity, and so that it's not doing the same thing from the right and from the left. So the best thing that we can say about the two-sided limit is that it does not exist. So that's the correct answer for this one. We can't really say that it's going to positive infinity because from one side it wasn't doing that, right? We can't say that it's going to negative infinity because on the other side it's going to positive infinity. So the two-sided limit, the best that we can say in this particular problem is that that limit does not exist.